Hello everyone. Today I'm going to share my latest research on Widevine. My name is Qi Zhao and I'm a security researcher from 360 Alpha Lab. And here is a brief introduction of myself and the team. And this is the agenda for today. Firstly, the introduction, backgrounds, and basics. And I will show you how we can find the vulnerabilities from Qualcomm PAs. And after that, we will learn the design of the shared memory model, which will be utilized to do the exploit. And after that, we will make an exploit based on the knowledge we have learned, and we will extract the key bugs from SFS and secured file system from Qualcomm. Finally, the closing. So why we are looking into Widevine on QTEE? Because both of them are high-value target. For QTEE, it have many devices running its chipsets, and it's very difficult to do the study and exploit. There are many regions, including this. The internal researchers from Qualcomm have done many works, and the so-called low-hanging fruits have been picked up, so make it more difficult to deal with. As for the Widevine, Widevine is a DRM solution provided by a company affiliated to Google, and there are billions of devices running it, and it has hundreds of partners. It will also affect many platforms, not just the QTEE, and it has become the de facto standard DRM solution for most Android devices. Here I want to talk about the basics of TrustZone in one page. The purpose to implement TrustZone is to do trusted computing in an untrusted environment and to protect high-value content. And the TrustZone features, including new modifications and as well as the reuse of existing processors and the possible use of TrustZone, including DRM, fingerprints, and key store. And there are many other scenarios. Now here is this picture shows the architecture of the TrustZone implementation on Pixel 4 XL. And the left side is a bit familiar. We have the user space, the kernel, and the hypervisor. And when the TrustZone is introduced, there will be a secure mode which has its own user space, kernel, and hypervisor. And to interact and switch between the two worlds, a secure monitor will be implemented. Okay, we are going to take a look at how user command is processed in Widevine. And here is the entry. And this is the user command buffer and its length, and the result from the TA and its length. And we'll look into this function, the dash command handler. In this function, in this line, we could find that finally a function will get called, and the pointer of this function is read from a global pointer, and also the bound check on input buff and in buff and out buff. The bound value is also read from somewhere near this pointer. So we find it and let's see what it will do. Well, in this, it is actually a table, and in this table, each entry will contain a command ID, the bound, and the function pointer. Okay, as we have find the function pointer of each command handler, we can look into each of them and find if there is any vulnerabilities. And then I find my first vulnerability, and this is the invocation graph of it, how to trigger the vulnerability. Okay, so the user command at first glance, it is a byte array, but of course it will contain internal structure. So I have recovered some of the structure as this. And the inner structures, okay, and this one, which is very interesting, the subsample metas. This is an array of up to 32 elements, and some of its fields have been recovered. So what are the subsamples and how are they processed? Okay, we got this metas, and each element of it contain offset and length information, which can locate them in ink buff and as well as thick buff. Both of them will contain many subsamples, and the next one and the next one. Okay, we have located this so-called subsample. So how are they processed? They'll get decrypted by this function, and in this function, if the do decrypt is equal to 0, the decryption will be demoted to non-copy. Like this, the decrypt process. So a summary of the subsample. The subsamples are embedded in the ink buffer and decryption buffer, and the length of and the offset of them are taken from the metas array, and when the do decrypt is equal to 0, the decryption will be demoted to non-copy. So, okay, we have already seen the vulnerability. Here it is. The subsample offset, there is no bound check on it. So with no bound check, the offset can be very big, and we can make a non-copy from an offset and overflowed place to another place. So we have got a vulnerability. The good news is it is accurate. It's non-copy rather than memory smashing. So we can do very accurate memory manipulation, and if we let the length equal to 0, equal to 1, we can make a single byte modification. The bad news is the subsample offset is a 32-bit value that is not big enough to cause integral overflow, so we cannot copy to the address lower than the ink buffer. And the ink buffer and the decryption buffer. So what's next? We need to find more information so we can turn this vulnerability to exploit. We need the address of the TA, and we need the address of our buffers, our shared buffers, and we need a delicate memory layout that can let our memory corruption reach the TA. So the first question, how is the TA allocated in memory? Actually, the memory range pre-allocated for TAs is defined in DTS file, and it's called the SIG-app region, which have a limited memory, physical memory, and limited range. So also the TA will use a linear map, which means that its physical address is equal to virtual address. Well, as the region is limited and it is fixed physical address, we can bypass the ASLR region brute force. We can keep trying to read from a page, and the page will crash. But if it doesn't crash, it means that we have reached some page belong to the TA, and we can prepare some signatures of each page, and we can compare it with the page we can read from and determine which page we have hit. So we can know the load base of the TA. And after that, we'll find how to know the address of the shared buffers we are controlling. Of course, we need the physical address of both of them. Before that, we'll take a look at how commands sent from the user space to TA. Here is a very basic send command API that contains no shared memory feature. It will have the send buffers length, and the receive buffer and receive buffer length. Okay, when the process is happening, it will call L control to the kernel driver, and the kernel will rotate to the TA. After the process, TA will write the result of this invocation to the receive buffer, and finally the kernel will return the result and the control to the user space. It's very simple and straightforward. But if shared memory is implemented, a new field will be introduced. Here, the QTEE com-infd info. It is actually a record that contains up to 4 ion buffers, which will tell the kernel that which part of the send buffer is actually a virtual address of shared memory. Okay, then in the kernel, the user virtual address of the shared buffer in the command buffer will be translated into physical address. I know this code is a bit confusing. I'll show you in the picture. I'll show you the user space to the kernel, and the kernel will make an SMC call to the TA. But before that, the kernel will translate the virtual address to physical address in the send buffer. And after that, the TA will return with the receive buffer field. And finally, the kernel will return the control to the user space. But before that, the physical addresses are wiped out for security reason, of course. So as the physical address will not get leaked to the user space, we need to find a vulnerability that can leak the physical address of the shared memory we are using. Here, we'll look into this function, the generate signature function. It is also a command handler in Widevine. And it will do this. It will copy part of the command buffer to the response buffer. And then this part of the response buffer will be used as a parameter to this function, the generate signature function. And then in the generate signature function, the parameter will get updated. But if there is an error, this function will return earlier and leave this value unchanged, which means that there will be a copy from the command buffer to the response buffer, and there is a chance that it will not get modified and will be returned to the user. So what if this part of the command buffer happens to hold the physical address of a shared buffer? Let's see what will happen. S0 user space to kernel and the kernel to the TA. It will do the translation and TA will return where the result buffer field and the value we want is copied to the result buffer. And finally, the kernel will return to the user space and get the physical address wiped out. However, a copy of it is left on the receive buffer. So this is the second vulnerability. It can leak the physical address of the shared buffer, and there are other similar functions that will have the similar situation. So we have know the address of TA and the shared buffers. So we need to find a memory layout that can let us utilize these vulnerabilities. Well, we have tried many approaches, many models, many plans, but they all have their own limitations. Here are some of my failed attempts. Here, we need a very huge buffer range that will contain the encrypt buffer and it plus an offset, and the decryption buffer and it plus an offset will reach the TA, and the memory copy will happen this way. It will need at least 3 buffers. Then to reduce the usage of huge buffer, we come up with this. We just need a very small range of buffer, and we let the encrypt buffer and decrypt buffer here, and the memory copy will happen from the TA to the TA. Well, however, as we don't have the method to control the TA, we will need to find up to 256 variants. We need this much different bytes of different value, so we can do an arbitrary byte write. Is also very difficult. And then the sandwich layout will let the TA between the encryption buffer and the decryption buffer, and the memory copy will happen this way. But it may need about 3 or 4 buffers. All of these plans have failed. But why? Firstly, we used the CNC command, which have vulnerability, and the buffer should get mapped to the QTEE before get used. Well, the CNC command will only register up to 2 buffers. So plans using more than 2 buffers are not possible. So, and also, even we have a way to get the physical address of an ion shared buffer, it doesn't mean that we can allocate an ion buffer with any physical address. Actually, the ion buffer have many limitations, and the buffers are carved out from the ion heaps. And here is how the heaps are defined, and only part of them are accepted by the QTEE. So we don't have many candidates to select from, make it very difficult to find a way. And finally, we get this one. I call it overlapping layout, and we'll let the encryption buffer plus its offset equals to the decryption buffer. And the decryption buffer plus an offset will reach the TA. Well, in this memory layout, we only need 2 buffers, and this ion buffering is relatively small enough so that we can let it fit in one of the scarce memory space we can get. And also with this memory layout, it's very easy to make read and write primitives. We just need to swap the encrypt buffer and decrypt buffer. So we have got everything, and we have a read and write primitive. It's time to post shell, I think. But however, in the TEs, there is no cell nor calculators to pop. So what should we do to show that we have achieved the exploit? And I find this seems that the vendor's high-value data exfiltration as well as code execution. So I think we can use code execution to exfiltrate high-value data from the Widevine. Here is the victim. The getDeviceID function, which will open and read content from a SLFS file and copy its content to malloc the buffer. Also, its file path is read from the global offset, which can be controlled by us, so we can use it to read any secure file system file available. We need to hijack the QCmalloc function with this getRobotNeeds version function, and this function will return a value on the global region, which is also controllable from with our write primitive. We can let this function return a value we want, that may be a pointer point to a place that we can reach out. So when the malloc happens, it will be located. It will return a buffer located in the global region that is readable for us, and then the file content will be copied to that place. And finally, we'll use a read primitive to retrieve the file content from that location. And here is a demo. Well, since the ASLR bypass is time consuming, so I just paste a screenshot here. And finally, the closing thoughts. Firstly, I think as a developer, I think metadata and data, when they get separated, it is very difficult to trace their relation, and will cause some errors, cause some vulnerabilities. And also, I think it's not a good habit to use a buffer that will be returned to the user as a temporary place to store important data or whatever is some transient data or whatever. Even you think that you will wipe them out, it's not a good habit. What if you forget to wipe them out? There will be information leakage. And as a security researcher, I think to explore and to understand a system so close-sourced as the QTEE, I know it's very difficult. So I use a hypothesis and verification workflow. I make some assumption, I make some guess, and I make a experiment and do the experiment and take a look at the return value to see if our hypothesis is right. With this function, I have find the internal logic of the system. And these are the people I want to say thanks to. And I also need to thank to you, my audience. Thank you for your time. And that's all of my presentation. Thanks.